So throughout these videos, we've been calculating the f value, and sometimes I've been dividing things by n-3 and n-2 and n-1, and I kind of said, look, don't worry about it. We'll talk about that later. Well, it's later now, so we've got to talk about it. All right. So where those differing numbers were coming from that we were dividing our variances by were because the variances had different degrees of freedom. So degrees of freedom is a bit of a thorny problem. It starts off with a pretty innocuous definition, right? So a statistic has X degrees of freedom if it requires a minimum of X independent pieces of data to calculate it, right? So the easiest one is the mean, right? The mean has n degrees of freedom in that the mean of a sample that has n data points in it, that mean has n degrees of freedom because you get one data point and you add it to the next data point and you add it to the next data point and you divide it by 3, and that's the mean. You need all 3 data points. Easy peasy, right? Now, if you think on a little bit, you might think, hang on, aren't all statistics going to have n degrees of freedom? And the answer is unfortunately no, right? So, for instance, the standard deviation has n-1 degrees of freedom. Now, why is that? Well, let me sort of put you in the right frame of mind. If I tell you that the door to my office is over there, the wall is over there, and I'm halfway between them, and then I tell you that the wall is 1 meter to my left, well, you now know how far the wall is. It's a meter away, right? So using logic like that, we can show that the standard deviation only has n-1 degrees of freedom. Well, why is that? Well, let's look at the equation, right? We calculate the standard deviation by taking the square root of the sum of each data point, xi, minus the mean of all of those data points. We square them, we sum them up, we divide them by n, right? So what does that mean? Well, it means that we don't need to know the last data point because the mean is exactly halfway between two. If we have n equals 2, it's exactly halfway between those data points. And so when you have calculated xi minus the mean for one, it is exactly the same for the other. And that is why the standard deviation only has n-1 degrees of freedom. You don't need the last data point. And it doesn't matter whether you got 2 data points or 100 data points. Once you've calculated n-1, you've done this this mean minus the data point for n-1 data points, you don't need to do the last one. And it turns out there's a lot of statistics that work on the same kind of logic, that once you've calculated something for all but one of the data points, you don't need to calculate it for the last one. There's enough information to calculate that last one. So the f-stat is, of course, the ratio of the explained variance to the unexplained variance. And these two statistics, the explained and unexplained, have different degrees of freedom. And the resulting f distribution varies massively depending on the degrees of freedom in those two variances. And let me just prove it to you, right? So we're calculating our F distribution in the way that I've done before, right? Where we're taking all of these samples, they're randomly distributed, but all from the same population, i.e. the null hypothesis is true. In this case, we have 4 groups, each with n equals 5. So the actual n is 20. And here we have 20 groups, each with n equals 20. And you can see that the shape of the resulting F distribution is very different. When we have small groups with small samples, we get this F distribution where all of the F values are pushed up against 0, while when we have lots of groups with lots of samples, the F distribution starts to look like a bell curve. And so you can see, that if we had done some test where we had these kind of degrees of freedom, these kind of group numbers and sample numbers, and we'd got an F of about, I don't know, 1.5. Well, in this situation, 1.5 is not that uncommon. But over here, 1.5 is pretty uncommon. So an F value of 1.5, if you had 20 groups, each with n equals 20, would probably give you a significant p-value, while in this case it wouldn't. Okay. So we know we need to know the degrees of freedom, but let me try and justify to you why the explained variation has 1 type of degrees of freedom, and the unexplained variation has a different one. Okay, and it's going to be a little hand wavy. You're just going to have to sort of go along with me here, right? Well, so what is the explained variation? It is the amount of variance explained by the coefficients in our model, right? And we remember that the coefficients in our model, if we had a one-way ANOVA with three groups, we have three coefficients. One of the coefficients would be the mean of one of these groups, and then the other two coefficients would be the difference from that mean, right? So we have three coefficients. And so we're explaining that variance with those three coefficients. So it sort of makes sense that the explained variance would have a degrees of freedom of about the number of coefficients there are in the model. And of course, it's k minus 1. It's the number of coefficients minus 1 for the same kind of, well, it turns out once you've explained the variation with the first two, you don't need to know the last one. The unexplained variance has n minus k minus 1 degrees of freedom, the total number of samples in the model minus the number of coefficients minus 1. Okay, and we can actually explain that pretty close. All right, so the unexplained variance, of course, is just the sum of all of the data points minus their means squared, all summed up, right? So for each group, how many data points are there in each group? Well, there are n over k, right? There's the total number of data points divided by each, divided by the number of groups, right? So there's n minus k. And in order to calculate the variance for that, then it will have that group, that one group, it will have n over k minus 1 degrees of freedom, right? And because then there are k groups, the whole thing has k times n over k minus 1 degrees of freedom, which is n minus k. And then, of course, we need to chuck on a good minus 1 for the same reason we've chucked it on everywhere else, that once we've known the amount of variance explained by nearly all of the groups, we don't need to know it for the unexplained variance due to all of the groups, we don't need to be able to calculate it for the last one. So if you didn't follow that, that's fine, because it was a little hand wavy. But the point is, you do need to know this equation, right? The F is the explained variance divided by its degrees of freedom, k minus 1, the number of coefficients minus 1, or the unexplained variation divided by n minus k minus 1, its degrees of freedom. And in a way, that makes sort of sense, right? Because we want to reward researchers using large sample sizes, and we want to punish researchers for using complex models. So it should be obvious why we want to reward n, right? So here are some data points, right? This is the amyloid beta in the plasma, actually, of impaired patients, impaired subjects, and people with mild Alzheimer's. Do you think these two are different? Right? This is n equals 6 and 5. It doesn't seem that different to me. Yeah, we've increased the sample size. This is real data, by the way. I mean, I'm still not very convinced that there's any difference here, to be honest with you. How about now? Okay, now I am convinced, right, that there is a real difference here. So it makes sense that we want to reward people for using a large n, right? And of course, the F value does, because the denominator is divided by n, and so as n gets bigger, the denominator gets smaller, and as the denominator gets smaller, this whole ratio gets bigger, right? So big n's lead to big F's. What about the explained variation? We divide it by k. Now, that punishes researchers for using complicated models. That may be less obvious why you'd want to do that. Well, the simple truth is that complex models always fit the data better, right? So this is a famous data set that I just still never know why it exists, which is the head length of brothers, right? It was collected in like 1890 or something. And you can see, unsurprisingly, that there is quite a good correlation. There is a significant relationship between the eldest brother's head length and the second to eldest brother's head length. Okay, and when we do this, we get an R squared of 0.505. Now, I just took that data and then just added literally a random number to this coefficient. Sorry, added a random number to the model and got the model now to fit a slightly more complex model, where it has one more coefficient that it just multiplies by that random number that has nothing to do with anything. It's just a random number. And now the R squared has gone up to 0.507. Right? And the reason you can sort of justify this to yourself is that let's assume, right, which you're probably going to assume, that the random number does not help fit this line, right? There's no information in there. Well, if that's the case, the model can call beta to 0, okay, and it will multiply this data by 0, and so it will be like it's never there, and so the R squared will be the exact same as the model was without this data included. However, if there's even like the tiniest hint where one of these numbers goes up, right, where one of these random numbers goes up, where the second brother's head length went up a little bit, then this coefficient can become positive, and it can just help explain a little bit of variance. So at worst, it doesn't make things better, but it always, in fact, is going to make things a little bit better. So it never sets that coefficient to 0, and hence it always explains just a tiny bit of something at sort of worst, and at best it could explain quite a lot, because sometimes random numbers do unfortunate things. And so you don't want researchers using overly complicated models, because overly complicated models always fit the data better. So that is why we punish for K.